So last time we talked about moduli spaces, and we used as an example the moduli space of all triangles. And we realized that triangles up to scaling and translation can be completely classified by fixing two angles. Now, we can also classify all kinds of objects. One of the most fashionable and fruitful ones have been elliptic curves. Now, you can write an elliptic curve in this form, where A and B are coefficients that can come from any field: the complex field, the real field, the rationals, integers, primes, and other finite fields. The j-invariant is a number with several different forms. So you might notice that if either A and oftentimes both coefficients come from the complex field C, that J would then be a complex number. And in fact, J can be any complex number with suitable choices of A and or B. And so we can classify elliptic curves according to their j-invariants. And it is not too hard to see that there are several elliptic curves for which their j-invariants are the same. And oftentimes an infinite number of elliptic curves can have the same j-invariants. So if we were to plot J, we would have at many different points an infinite tower, an infinite family of elliptic curves. And that is true at every point. Knowing just the j-invariant of an elliptic curve does not give you necessarily all the information that you would need to analyze that curve. But it does tell you where in the moduli space it lives and what family it belongs to. And so you could probably tell by now that J is isomorphic, or we should probably say that the moduli space of elliptic curves is isomorphic to the complex plane. J can be any complex number, so it would trace out the entire complex plane, and so it would be isomorphic to the complex plane.